Now I'm going to take a little bit of time to talk about all of the liquid properties, put them all kind of in context together, summarize what we've done so far. So the vapor pressure, surface tension, viscosity, and capillary action are all properties unique to liquids. Liquids, solids, you can't really have molecules leaving. There's not enough, so you can't have really vapor pressure, surface tension. In order to create new surface, this idea of flowing, you can cut solids, and how difficult it is to cut a solid is based on the interactions between molecules. But surface tension, this idea of this variable surface tension, that's continuous variable, it can be whatever the liquid wants it to be. A liquid can adjust. It's unique to liquid. Viscosity, flow. You're not flowing a solid. And capillary action, again, it's all about flow. And so these are all unique properties of liquids that we can all understand and predict based off of intermolecular forces. For vapor pressure, surface tension, and viscosity, we want to be able to predict relative ordering, again, what's higher, what's lower, between similar molecules, just like we did for boiling point. And then capillary action is more just kind of there. It's not really something you can predict. Liquids just do it. And then it's again related to, say, polarity, again related to intermolecular force. Which one has a higher? How do the polarities match in terms of that adhesion that we could potentially see? So these are all related to intermolecular forces. What that means is we can start to relate the properties of compounds to other properties of those compounds without knowing anything about the compound. So let's look at an example. If compound A has a higher vapor pressure than compound B, which compound has the higher viscosity? This is the type of prediction we really want to be able to make. This is telling us, we know one physical property, vapor pressure. What else do we know about that compound? We can start to know all of the properties of the liquids, at least relative, if we're dealing with two compounds. So if I want to know higher viscosity, right, which compound is the higher viscosity, in order to relate that between compounds, I need to know how it relates to intermolecular forces. And we know that strong forces lead to higher viscosities. Those are, remember, thicker liquids. They don't flow very well. Okay, so then we know that if I have, in order to determine the higher viscosity, what the question really is which compound has stronger intermolecular forces? Well, I don't know what the compounds are, so I can't draw their Lewis structures. But I do know the vapor pressure. I know that compound A has a higher vapor pressure than compound B. So how does vapor pressure relate to intermolecular forces? High vapor pressure means you have weak forces, right? This is kind of the opposite one. Everything else is direct, strong, high. But it is the opposite. High vapor pressure means weak forces. There's lots of molecules in the gas phase, means they're not held together very well. So we are told that A has a higher vapor pressure. That means compound A necessarily has weaker forces. If A has weaker forces, that means it has a lower viscosity. It is runnier than compound B. Compound B, therefore, has a higher viscosity. It is a thicker liquid. It's harder to flow, it's harder to pour, slower to pour, all of those things. And so we can see that this has nothing to do with, we don't know what compound A and compound B are. This is just generically always true for liquids. Every liquid, and if ever you have a liquid with a higher vapor pressure, that liquid also will have a lower viscosity. These, because they're all related to the same idea of intermolecular forces. And so this is kind of, we've built up all this world of intermolecular forces, but this really tells us everything, right? We don't need to know anything about what types of forces are or do any sorts of relationships like that. We can just take some physical properties and predict all of the others. Again, this is kind of one of the goals of chemistry, where we can take a little bit of information about a compound and stretch out what all information can we get from that. We're trying to avoid doing experiments. You do one experiment about, say, vapor pressure here, and you can get information on viscosity and surface tension, boom, right away. At least relative information, which is really useful. Participation 116, question 4. If compound C has a lower surface tension than compound D, which compound has the higher viscosity?
This is the fourth question on participation 116, due Friday, January 16th at 11:59 p.m. over on Blackboard. Link to the assignment is below the document where there are the links to these videos. Again, if compound C has a lower surface tension than compound D, which compound has the higher viscosity?
So one of the other kind of factors that we haven't really touched on at all is the idea of temperature. And temperature affects all intermolecular forces in the same way. And basically, as your temperature increases, intermolecular forces become less important. Okay, so we've seen previously this applied to boiling point, that when you have higher temperatures, you can get things to leave the liquid and go into the gas. And the temperature that happens at is based around, the strength of intermolecular forces. But eventually, you get to such high temperature for anything that it's just going to boil. Because the molecules are just moving more, so even in the liquid phase, they're all just kind of bouncing around, so there's not really strong interactions. And so, for our other liquid properties, increasing the temperature always decreases surface tension, decreases viscosity, and increases vapor pressure. Molecules are just moving more, so they're more willing to move to the surface, easier to flow, you have less connections between molecules, and they're moving faster, it's more likely they escape into the vapor phase. And so this is going to always affect it. And so one of the common applications of this, one of the most important viscosities, is the oil that's in your engine. And so if you've lived in various different climates, you will know there are different types of oils, and those correspond to basically different sizes of molecules, which corresponds to where those molecules are going to have an appropriate viscosity to serve as a lubricant in your engine. And so when we're looking at this, you're going to need different sorts of molecules that have the appropriate viscosity at different temperatures. So this mostly affects here we're generally fine, but it mostly affects it if you've ever lived in a cold climate, especially a very cold climate, where you need to get special oil that will exist as, say, a liquid in cold weather. And so that's really important. You also want to have for it not to get so hot, because eventually, if it's super hot, then there's just no viscosity at all, and it's just like you have water in there. So you do want to make sure you have this oil. So that's an important application where there are some variable temperatures, and again, it's predictable. You always decrease surface tension, you always decrease viscosity, and you always increase vapor pressure. Doesn't matter what it is. So volatile liquids become more volatile. Everything flows smoothly.
And that is gonna do it. There was 4 questions on participation 116, including 1 in this video, but there's 4 throughout this set. You want to find all 4 questions, get them answered, and get those answers submitted over on Blackboard. There will not always be 4. There will be a few number, 3, 2, 3, 4, 5, depending on the set of videos and how long each of the questions is. But they're all 4. You want to get all 4 of them answered. Some of them had multiple parts, right? 1 was like 1 and 2 were like ABC. So 1 ABC, 2 ABC, 3, 4. That all needs to be answered over on Blackboard. Over on Active for Saturday, you got the week 1 homework due. And then on Sunday, you need to complete the post lab for the endothermic versus exothermic lab. There's a rubric you should check out on the on Blackboard of how to do it. There's a video I posted of how to complete the post lab. So if you have any questions about any of that, let me know. Otherwise, answers will go live. Answers will go live to the participation. I forgot that. On Friday night after the participation's due at midnight, there will be a video that will pop up right below the participation assignment with the answers. Check that out. Otherwise, that's it for me. Enjoy your weekend. I'll see you next week. Bye-bye.